Konstantin Zarembo from Nerdita Integrability on the Coulomb branch. Please.
Thank you very much. It's a great honor for me to speak in this conference dedicated to the work of Rodney Baxter, which has been a continuous source of inspiration for my work. This is probably the most important equation I've learned as a grown up. Yes. So I came to work on integrability by chance. I haven't learned it as a student or as in the graduate school, but it somehow naturally appeared in the study of the safety correspondence, which is the duality of string theory in anti-de Sitter space and gauge theory in 4 dimensions. And it already appeared in the first talk today by Charlotte, but let me still repeat the main ingredients of ADS-CFT. It relates a weak coupling regime of one theory. For instance, if you take string theory, then weak coupling would be when the string tension is very large, to the strong coupling regime of the gauge theory, because string tension is proportional to square root of the gauge coupling. And so for the string tension to be large, the gauge coupling should be very big. And vice versa, when the gauge coupling is small, and in the perturbation theory, string theory becomes very quantum, very strongly coupled. And so in the intermediate regime, both sides of this duality are equally complicated, and it becomes inaccessible to direct analytic analysis. But it turns out that this system turns out to be integrable, and there is one can trace interpolation at any coupling by the methods that were pioneered by Rodney Baxter of beta ansatz and TQ equation, and which in this context they are known as quantum spectral curve. There are new ideas of how to use how to compute correlation functions using integrability. What I will talk about has to do with the boundary generalization of the Yang-Baxter equation. So if the system has a boundary, then apart from the S matrix, it contains also, or R matrix, it also contains the reflection amplitude, which also has to satisfy consistency conditions. And as the Yang-Baxter equation, consistency conditions are usually sufficient to determine the reflection amplitude just from the symmetries of the problem. In string theory, boundary means that the string can end in some hypersurface in space-time, in anti-de Sitter space. And in string theory, this hypersurface is called the D-brane. So D-brane, of course, can either break integrability or preserve it, because reflection of the D-brane may create particles, and then integrability will be lost. But in some special cases, reflection remains elastic, and then integrability is preserved. And there are many instances where this can be used to deeper understand the idiosyncratic correspondence. And in the talk by Charlotte Christensen, that this setup was used to study integrable defects in the gauge theory. So the deep brain in that case intersects the boundary on a line or on a surface or at a point, and this point serves as a defect in defect operator in conformal theory. But in ADS-CFT, it can be studied by the methods of integrability if the deep brain preserves the integrable structure. I'll talk about the setup where the deep brain doesn't intersect the boundary and it floats parallel to it in anti-de Sitter space. So this space has an extra coordinate z, the holographic radius, in addition to spacetime's coordinates x. And one can consider a deep brain that is parallel to the boundary, so it sits at a fixed value of the radius. So in gauge theory, that corresponds to spontaneously breaking gauge symmetry by an expectation value of a Higgs field, which can be related to the distance of the deep brain from the boundary. So there is an inverse relation that can be justified by considering a static string that stretches from the deep brain to the horizon. So what can be computed in this setup? So one set of observables that can be studied are one-point functions of local operators. So a local operator is an eigenstate of the string Hamiltonian. It can be, well, it emits a string, closed string that is then absorbed by a deep brain. And because it can be absorbed in the bulk, the operator can have a non-trivial condensate, a one-point function. So from the worldsheet point of view, the one-point function is equal to an overlap of a boundary state associated to the deep brain and the physical state of the string that's associated with the operator. And if the deep brain is integrable, then we can use integrability tools to compute these overlaps and hence the one-point functions. So what are the integrable boundary state? Well, the notion was introduced by Goshen and Zamolodchikov many years ago. And it basically relates the open and closed string channels on the integrable system. So if the boundary is time-like, then naturally particles will reflect off the boundary. This reflection has to be elastic for integrability to be preserved. But if you go into the frame where the boundary is space-like, so we go from the open string channel to the closed string channel, then these reflected particles become particle pairs created at the boundary. And elasticity means that each pair has an opposite momentum. So an integrable boundary state is a superposition of paired states, so where each particle has its pair with opposite momenta and the same quantum numbers. So there is a very beautiful theory that goes back to the work of Tsuchiya and Jean-Sébastien Coe and his group in Amsterdam. that computes overlaps of integrable boundary states with beta eigenstates, physical states of the system. In terms of integrability, has this shape, so it has a universal piece, which is a superdeterminant of the Gadan matrix. I'll explain. It actually appeared in Charlotte's talk, but I will remind you what the superdeterminant is. And a simple prefactor that is state-specific, and it essentially can be expressed through Baxter polynomials of the beta eigenstate. So let me say a few words about the Gadan superdeterminant that appears here. So the Gadan matrix is the Jacobian of beta equations. So if you write beta equations as the phase equal to 2 pi m, then the Gadan matrix is just the derivative of the phase with respect to the beta rapidities. Now, for integrable boundaries, the Gadan matrix has an extra structure because so the integrable boundary states have overlaps only for paired states where each rapidity has its pair, which means that there is a Z2 symmetry that acts on rows and coulombs of the Gadan matrix. Once we have a Z2 symmetry, we can define a supertrace and a superdeterminant. So it has nothing to do with supersymmetry here. It's just a exploits a Z2 invariance that is necessary for integrability. So of course the superdeterminant can be easily computed because the Gadan matrix for paired states have a symmetric structure, and then the ordinary Gadan determinant will factorize due to the this block structure of the Gadan matrix. So the superdeterminant then is defined as the ratio of the factors. And it is this object that appears in the, this is the universal part of the overlap with integrable boundary states. So returning back to the gauge theory, the setup we want to study corresponds to the Higgs symmetry breaking of the gauge symmetry. So the gauge theory at hand is contains gauge fields, fermions, and 6 scalars, all required by supersymmetry. And the scalar potential is the trace of the commutator squared. So if the matrix, the scalar fields are diagonal matrices, then the potential is exactly equal to 0. So the theory has a modular space of vacua, which are just diagonal matrices, and this space of vacua is usually called the Coulomb branch. So the origin of the Coulomb, the origin of the space of vacua is where the expectation value is 0. Is a conformal theory, conformal point, and in general, on the Coulomb branch, the conformal symmetry will be completely broken, but I'll consider the simplest case where the Higgs field has only one non-zero expectation value. In that case, the symmetry is broken from SUN to SUN minus 1. And so the fields will have a big massless block. So in the large N limit. That's always consider by default. That's where string theory operates. So that this massless box is very big, and fields there are still massless. So the interactions in this theory are basically through massless fields. So the off-diagonal blocks are massive W bosons that get mass by the Higgs mechanism, and then there is also a dilaton which forms the whole multiplet of supersymmetry. But it will not play an important role in my discussion because I take the large limit, and this is just one component of the fields. So the ADS dual of this, as I said, is a deep brane in the bulk that's parallel to the boundary, and one can match the action of the string that goes off to infinity to the mass of the W boson, and so this gives a relation between the Higgs wave and the distance of the deep brane from the boundary. So this setup can be shown to preserve integrability. That's a non-trivial calculation. It was done by Ron Dimyacha, who is a master student from Stockholm. So one may expect that this setup is integrable, and then one can use the machinery boundary integrability to compute correlation functions. So I'll concentrate on the one-point functions, the vacuum condensates, which will basically arise because of the Higgs symmetry breaking. So let me give an example. So of course this theory doesn't have genuine mass parameters, so the only mass scale in the game is the Higgs expectation value. So all the condensates should be proportional to, so their dependence on the expectation value is dictated by their scaling dimension, with the prefactor that is the dynamical object that we want to calculate. So let's consider the simplest example of the mass operator. It's called Kanish operator for radical force parameters. So at the leading order, we just substitute the expectation value for the fields, and so the expectation value is just equal to v squared. But then we also need to take care of normalization. So usually, as always in conformal theories, we normalize the operators by the two-point functions. So we need to divide by the two-point function of the operator. And so this gives some coupling constant dependence from the loop diagram that normalizes operator to 1. Okay, so this formula, of course, is tree-level. It's valid at recoupling. There are corrections. It's power series in G squared. Before discussing these corrections, let me generalize this calculation to arbitrary scalar operators. So we can consider an operator that's built of L scalar fields. So we can multiply them and take the trace to make the object gauge invariant. And tensor as a wave function of a spin chain. So the operator then is regarded as a collection of L spins. So spins here are simply vectors in 6-dimensional space. And the renormalization of the operator, so these operators, they need counter terms, and they start mixing as a result of renormalization. And this mixing is described by an operator acting in the space of the spin chain and happens to be the Hamiltonian of integrable type. So instead of diagonalizing this operator, we can, so the problem of diagonalizing this operator is solvable by beta ansatz. Well, the beta equations can be written in terms of the group theory data. So the Cartan matrix of SO6 and the weight vector of the vector representation. And once these equations are solved for beta rapidities, the anomalous dimensions can be simply calculated by as an energy of the beta of the beta eigenstate, beta eigenvalue of the spin chain. So what about the expectation value of the condensate of this operator? Well, again, we can at tree level we simply replace fields by the Higgs expectation value, and this picks up one component of the wave function psi. So let's say that the vector is directed in the first, let's say it has components 1, 0, 0, 0, 0. Then the expectation value will be proportional to the psi component with spins in the one direction, psi 1, 1, 1, 1, 1. So we can think of this as a projection of the wave function on a particular vector. So in this case, this is just a north vector of component 1. There's also some normalization factor here, which is not really important. So the upshot is that the one-point function is an overlap of a beta eigenstate. This is the eigenvalue of an integrable Hamiltonian with a particular state which is not an eigenvalue, but which actually happens to have nice properties. So one can show that this state belongs to this type of integrable boundary states. It only contains pairs of particles. And so this wonderful theory of integral overlaps can be applied to this state as well. And actually for this particular state, the overlap formula was known. It was derived by these authors with no particular goal, just because they realized that this state is integrable. This really simple expression in terms of the beta roots. So once you give me the beta roots, I can calculate the condensate of this operator by simply computing the Godin matrix and taking its superdeterminant. And then taking some products of simple functions of beta roots. So it's completely algebraic. And well, here is the explicit expression for the Godin matrix. So this basically solves the problem for computing tree-level overlaps for scalar operators. So what about arbitrary operators that contain gauge fields and fermions and derivatives? Well, then one can exploit symmetries of the problem. One doesn't need to do a separate calculation. So we know how the overlap looks for the SO6 part of the spectrum. To generalize it to all operators, we just need to extend SO6 to the full superconformal symmetry of the theory, which is PSV22/4. And it has this Dynkin diagram. It's a supergroup, so it has fermionic nodes in the Dynkin diagram. And actually, this Dynkin diagram is not unique. this not uniqueness is not a bug, it's a feature. It actually allows one to relate overlaps in different frames of where pretend matrices are written differently. And this superdeterminant in particular has nice transformation properties under these fermionic dualities, and they allow one to completely fix the overlap once part of it is known. So if you know the SO6 part of this formula, so I don't know if these notations are clear. So this is the arguments of the Q functions. So these products here can be written as Q functions at particular arguments. So this is the Q function at 0, this is at I over 2, and so on. And so these are the Q functions appearing in the numerator, and these are in the denominator. And it turns out that the extension to SU4 is essentially unique if you require nice transformation properties under fermionic dualities. So if you go to higher loops, it turns out that, again, we don't need to do any tedious loop calculations. It's enough to use integrability. So the spectral equations at high loops are known. These are known as asymptotic beta ansatz equations. Then the Gadant part is simply the Jacobian of these exact non-perturbative equations, and the Q functions can be generalized accordingly. But there is one additional ingredient that is not fixed by this three-level structure, and this is a reflection phase of the boundary. So that has to be determined separately, but this can be done by the usual integrability bootstrap by imposing analyticity, unitarity, and crossing on the reflection amplitude. And this in the paper by this Karanada and Komatsu, and actually basically the same expression appeared in the earlier paper by Komatsu and Wong. So that who considered the main wall defect in n equals 4, but then it turns out that by taking a particular limiting procedure from that expression, I can get the Coulomb branch reflection amplitude. So you see, it's a fairly complicated function. You can expand it in power series. Then what you get is logarithms and the Euler gamma that comes from the expanding the gamma functions. This dressing phase will appear in one-point functions through the prefactor. In particular, from that one can deduce what would be the one-point function of Kanishka. So we can also write an exact expression, but we can expand it in the coupling constant as well. And this expansion nicely matches with the direct computation, so that the first term is just the three-level answer that I started with. And the second term is the loop correction, and it comes with the right coefficient. So with that, I would like to thank the organizers again for putting together this nice event. Thank you very much.